Welcome everyone. For today's prep, I want to look at another example for figuring out the domain of a power series. So we have the power series in this example. It's the sum from n equals 0 to infinity. Our coefficient term is the n factorial, and then our power of x term is this x minus 3 raised to the power n. So we've got this power series, and essentially we want to find the domain. So we're going to figure out the radius of convergence and the interval of convergence for this power series. All right, so how we normally start these off is we start with our ratio test. So let's do exactly that. Let's start setting up our ratio test. So that's normally the first step. Ratio test setup. All right. So we're doing our ratio test setup here. And what gadget do we calculate for the ratio test? Well, it's that absolute value term of an plus 1 over an. All right, so it's called the ratio test because we're doing a ratio. All right, so let's start by looking at an plus 1. So we go to our terms in our series, and wherever we see an n, we're going to change that to n plus 1, parentheses n plus 1. So if we do that, we'll have the n factorial will become parentheses n plus 1 factorial. And then our power term will be x minus 3 raised to the n plus 1. All right, so that's our n plus 1, an plus 1 term. Now, in our denominator, we're going to do just the original terms from our series, so just an. And notice, normally when we do this, when we go through the setup here, we normally do like a separate fraction for each an plus 1 and an. But because our series doesn't have a fraction, we don't really need to do that. So in the denominator, we'll have our n factorial times x minus 3 raised to the n. Okay, so now we want to simplify this down. So we group similar terms together. And actually, we kind of already have them grouped pretty nicely. So we have these powers of x terms here, and then we have our factorial terms. Now, let's remember what's going on with these factorials. When we go to simplify, normally you want to compare your factorial terms. So when we're doing the ratio test, if our coefficient has a factorial, then we should end up with at least 2 factorials. And you want to pick the one that has the bigger face value. So the larger face value here is n plus 1. And let's just think about what that would be. So n plus 1 factorial. A lot of times it helps to just start writing it out. So the top page here is n plus 1. Let's flip the page. So we'll have our n plus 1, and then what's underneath it? Well, it's page n. So we'll have n factorial. All right, so now if we look, this n plus 1 factorial has an n factorial that's kind of built into it. So when we go to cancel, the n factorial in the denominator is going to cancel that off that n factorial from the numerator term. And then when we simplify these powers of x, we've got n plus 1 copies in the numerator, and we've got 1 less in the denominator. So we'll have, after we subtract the exponents, we'll have just a single copy of x minus 3. So what happens after we simplify this? Well, we'll have our absolute value term, or we'll have our x minus 3 term, and then we'll have n plus 1 left over in the numerator. So we'll have our n plus 1 left over from the factorial, and then we'll have 1 copy of x minus 3 left over from the power term. Now, what about this absolute value? Well, if we look, the n plus 1 here is positive. So the only thing we don't know the sign of is this x minus 3 term. So it's a property of absolute value that when we have absolute value and there's multiplication in the middle, we can split up the absolute value sign. And since n plus 1 is positive, we don't need the absolute value around there. So we only need the absolute value around that x minus 3. All right, so now we have our ratio test set up all nice and simplified. So now we're ready to calculate the ratio test limit. So we calculate the limit of this gadget, and we'll use our simplified term as n goes to infinity. So we'll do the limit of n plus 1 times this absolute value x minus 3. And when we do this limit, we want to remember n is the thing that's approaching infinity. So that x minus 3, in the context of that limit, that x minus 3 is just a constant term. So we want to think about what happens to this expression as n gets bigger and bigger. Well, in most cases, we're going to have to break this into cases because the limit's going to behave differently depending on what this x minus 3 term is doing. So let's suppose that x doesn't equal 3. So let's suppose x doesn't equal 3. Well, then x minus 3 is not 0. So this is just some number, some positive number. All right, so if this is just some positive number, well then if n is getting bigger and bigger, n plus 1 is also going to get bigger and bigger. So we have this one thing that's getting larger and larger, going to infinity, and we're multiplying it by just a positive number. So the result's going to be still go to infinity. So that limit is going to be infinite if x doesn't equal 3. Now, what happens if x is equal to 3? Well, then this x minus 3 term is going to be identically 0. So it's going to be exactly equal to 0. So n is getting larger and larger. So n plus 1 is going to be getting larger and larger. But each time we do that, we're going to be multiplying by 0, exactly 0. So the result will just be 0. The limit will just be 0 because no matter how large n gets, when you take a number and you multiply it with something that's exactly 0, you get 0. Now, just a little note here. So when we were doing limits, there's an indeterminate product. So when we do limits, there's an indeterminate product where you have one term that's approaching 0 and another term that's getting larger and larger. And this is indeterminate because we don't know if the term that's approaching 0 is going to win or the term that's approaching infinity is going to win. We don't know. This one is different, though. What we're seeing here is different. We're not seeing something that's approaching 0. We're seeing something that's exactly equal to 0. And that's a difference. So in the indeterminate product, the term that's we're saying is 0 here, this is approaching 0. And that's different than what we have here. When x is equal to 3, this is exactly equal to 0. So that's why that's not indeterminate, because we know this is exactly equal to 0. It's not just a small positive number. This term is exactly equal to 0, which will cancel off any number that we multiply with it. So just a little note here. An indeterminate product, when we say 0 times infinity is indeterminate, that 0 term is not exactly equal to 0. It's approaching 0, but it's not exactly 0. So that's different than what we're seeing here. X minus 3, in the case when x is exactly equal to 3, this is exactly 0. So it's not indeterminate. All right, so we've done our limits. And one of these, what's the inequality for ratio test? So let's remember our inequality for ratio test. So it converges when the limit L is less than 1. And it diverges when the limit L is greater than 1 or is infinite. And so we see, well, this kind of fits nicely with our two cases here. So in the case when x is equal to 3, our limit L is 0, so that is less than 1. So we see that it converges when x is equal to 3. And it diverges when the limit L is bigger than 1 or is infinite, and that's what we're seeing here. Infinite when x is not equal to 3. All right, so we have it all. There's no edge cases to consider here. We've essentially considered all possible x values. So now we just have to write out our answer. So the interval of convergence, this is just the set of all x values where we have convergence. And we found that there was only one x value. So there's a way to write an interval or a set with just one number in it. So there's a few ways we can do this. So our interval of convergence, we can write it as the singleton set. So curly bracket 3. Or if we wanted to write it as an interval, sometimes we'll see this, the closed interval from 3 to 3. So that's the only interval containing just that one point. And then our radius of convergence is the size. Remember, the radius of convergence is measuring the size of this interval. Well, what's the width of this interval? 0. So the radius of convergence is 0. So our radius of convergence here is 0. So when the radius of convergence is 0, that means we're only converging at the center point of our series. And that's what we're seeing here, really, is if we go back to our power series, x equals 3 is the center. So you always get, for a power series, no matter what the coefficient does, you're always going to get convergence at that center point. And then from there, it becomes a question. So you are always guaranteed to have convergence at the center point. And that's because when you plug the center in, you're going to get 0. So it's like we're adding up an infinite number of copies of 0, which we can add up 0 as many times as we need to. The trouble happens when this is not exactly 0, and then you have the coefficients playing a role. All right, so just another case of example for interval of convergence and radius of convergence. And in this one, we're seeing an example when we get the interval of convergence just to be that center point, and so our radius of convergence, the size of that interval is just 0. So we'll be practicing more of these in class. So we'll have some fun on Monday. We'll see you then. Bye-bye.